Hi, thank you very much first to all the .mesh people to put this together and for the invite. My name is Tania. Oh, well, there is a link to these slides if any of you want to follow along or check them later. At the moment I work as a data engineer at Hello Soda, but before I have been working as a research software engineer at the University of Leeds, the University of Sheffield, and also do additional consulting jobs for data science teams or machine learning teams that want to increase their reproducibility. So really, what I do is, I'm a reproducibility nerd. I try to get people to jump onto the wagon with me. But I'm also a software carpentry trainer and instructor. I love open source software. So I'm more like an advocate, a community builder for the open source community. I'm a contributor, maintainer, and consumer as well. And I just love emojis and memes. So you're in for a ride if you've never seen any of my slides. So far, our previous speakers have highlighted how much research has changed. And in the last few decades, because we have so much more data, we have so many more computational resources, we have so many new tools, that has led to a change in science. It has led to a change in how we actually conduct research. But we often, something I can't stop but wonder is whether larger data sets and more powerful resources are actually natural bedfellows and how they play together. The truth is, they do pair really well, but not always. On one side, large data sets and complex models allow us to do more rigorous, better science, do more subtle scientific phenomena discovery. And we all know that we have more access to data than ever before. We have so many computational resources that basically the sky is the limit. We can do and study phenomena that were very out of our reach before because we just didn't have all the computational power that we have nowadays. The problem is that us relying so much on computers now, relying so much on data, means that the previous way to disseminate our results and our findings are just not enough nowadays. And also it has forced new paradigms in research to emerge in data science. So I'm just going to throw in this question, who cares about reproducibility here? And I guess this is the right audience. Yes. So this is me, basically. That's all I care about. Well, some of the things I care about. And the truth is, I hear now more and more teams and more people talking about reproducibility and saying, well, I want my research to be reproducible. I want my team to have best practices. But the truth is that many of these data scientists and researchers don't actually include these research best practices in their day-to-day work. And the truth is, because we talk about reproducibility, but we're not on the same page. Laura said that reproducibility can be different, and yeah, it's true. If you ask a computational researcher, he or she will have a certain vision of what reproducibility is. Experimentalists will have a different vision of what reproducibility means to them. So in experimental sciences, let's say in a more traditionally experimental framework, reproducibility is always associated to the method and your environment to produce a certain set of results. So you can talk about experimental reproducible science if you can get the same results following a certain method, even if you do the same study in a different laboratory. So you can have someone in Oxford doing a certain study and have someone in the MIT, for example, following the same recipe, the same methodology, and get similar results or very similar results for a certain research question. And when I talk about experimental reproducibility, I always refer back to Pasteur because he's one of the pioneers in this area. Around 150 years ago, he started doing all of his studies, and he was very methodic in the way he was documenting everything he was doing. At that time, his peers didn't believe in that. There was a certain resistance to this exhaustive documentation of experimentation. So basically, you would have his notes with every single step, every part of his methodology reported, what worked, what didn't work. But eventually, their peers, his peers, realized that if they follow his recipe as it was written down in his notebooks, they could get the same results. And thanks to this approach, we have now antibiotics. We have a higher life expectancy, and we can cure some diseases that were incurable or deemed incurable some years ago. And we can also drink beers without dying. So when we change this paradigm of having experimental science and reproducing a recipe and following step by step, and we start working in a more computational environment in which we change, I don't know, our machine from being a laboratory or a clean lab into being a laptop or your HPC or your Amazon instances. Reproducibility refers to being able to get the same results on your own computer or other instance using the same code or the same version of code, even after a few years, a few months, a few days. So computational research, for it to be reproducible, has to be time and machine independent. So up to now, I have said you have to provide the same codes to get the same results. So where does the data fit in this very small pipeline? And I'm going to talk about different layers, because so far I've said the word reproducibility so many times. Laura did a very good job of explaining what reproducible science is. But if we were to think about those three components also that Luke mentioned before, that is code, data, and environment, let's say that I run a study and I have that data there. I have my code, my environment, and when I put all of these three bases together, I get a certain result. If I were to pretty much give that to somebody else, run the same data, the same code, the same environment, their results should be the same, and that is reproducible. So it's like one-to-one comparison pretty much. If I wanted my study not to just be reproducible but replicable, then I can have my data, my code, my environment, and someone probably in another part of the world will be collecting data on their own. So they compare their own data with my code and an environment to get similar results for the same research question. And this is very important. It has to be the same research question that they're aiming to investigate. We can go a step further and aim for robust studies. It gets harder because not only you'll have your data and your code and your environment, but somebody else might be collecting their own data and probably prefer different tools. So probably I'm using the same algorithm or the same theory, and I prefer using Python, and my peer prefers using R. If it's the same methodology, if it has basic standards on how to conduct our research, we should be able to talk about robust studies. There is an additional layer that is generalizable research, but that is very, very far from what we can currently achieve. So I would say that from these three layers, the current state of data science and research and science is barely scratching this surface of reproducible research. And this happens because doing reproducible research is hard. And a lot of people think that it is black and white. Either your research is reproducible or not. But as Peng did very well in explaining that it's not black and white, but rather it is a spectrum. And you can achieve within these three layers of reproducible, replicable, robust, you can achieve two different intermediate steps and intermediate layers. So the current standard of research, or the standard to disseminate your results, has been doing your research, getting your results, publishing out in a paper so that your peers could understand and reproduce your science. But as we have been changing the way we conduct research, the publication only is not reproducible, because there are so many other things that are hidden and are often obscured by just publishing a paper that you don't have enough knowledge and enough tools to reproduce this study. So you can start adding additional layers or additional bases. So you can introduce your publication plus your code and move a bit towards replicability and reproducibility. If you then add your publication plus your code plus your data, you're doing a better job. And then the ultimate goal is providing publication, your linked and executable code and data. So I'm just gonna, normally I like collecting failures or examples of data went wrong, software went wrong, project management went wrong. But I want to introduce you to some examples on how we can move across these reproducibility scheme, or this reproducibility spectrum. So if we look at something like low reproducibility, we get the paper only. In theory, if you write a good enough paper that provides good enough details about your methodology, anyone else should be able to follow along and reproduce. It is not easy, and in most of the cases it is impractical, because there is only as much information you can put in there. You can't lay out every single step that you did. And there's also these conceptual dependencies that needs to be covered for you to be able to reproduce this study. And these conceptual dependencies refer to technical knowledge, like being able to use certain tools, and also some background knowledge. So you need certain specific mathematical knowledge, I don't know, physics, or discipline-specific knowledge that otherwise you wouldn't be able to reproduce, say, the study. An example of this is this paper, and they only provide, they said that they developed some software or some scripts to get to the results, but there is no evidence. There is no data accompanying this paper. There is no code, so you can't verify that the results are accurate. Then we can move to a medium reproducibility layer that is providing the code and the data. At the moment, the International Conference of Machine Learning and some other journals and some founders are starting to move towards this. So some founders are starting to say, if I'm going to give you my money for you to develop X study, then you should at least make your code and your data public. An example of this approach is this paper. They got a special mention at ICML 2017, and you can go there to that GitHub repository and find their code and the methodology they followed that goes together with the paper. And finally, the high reproducibility is, as we've all highlighted, providing your code, your data, and your environment. So when we talk about environment, it is providing all the libraries, all the dependencies that will allow you to run the code in any machine. And it will help you to avoid it runs on my machine problem. A good example of this is this paper from Wei Con and Liang. And they gave two options. They provided a hosted server that is the very first link, and they also provided a Docker image. So if people don't want or are not technically literate enough to use Docker containers and generate an image from a Docker file, they have the other alternative, that is this the server-hosted version. So all people need to do is click on that link, and they will be taken to an environment in which they can see and interact with their results. But achieving this kind of technical literacy and commitment to reproducibility is very hard. And so often when I talk to researchers, one of my jobs is to convince researchers and data scientists to aim for this, to aim for something like this. I always get questions like, well, why even try? Why should I bother? Why should I do it when the 80% of 90% of my peers are not doing it? First of all is to make the best of convention. Jenny Ryan calls it like agreeing when we're going to decide, when we're deciding that we're all going to drive on a certain side of the street, and it allows you to progress. When you have established conventions in your laboratory or in your group, you know where everything lives. So you know that if you have 50 models or 50, I don't know, research studies, you know that every of these studies will have a similar file system. So if you're looking for the data, if you're looking for the documentation, for the figures, you know where to look. So you don't have to guess and find, and probably not actually find what you're looking for. This helps a lot when you have staff coming and going, and this happens a lot in academia. You have a postdoc that is working for you for a year or 2 years, and then this person leaves. So if you have a convention, an established handover, an onboarding method, it makes it easier. You retain your institutional knowledge. So all of that work that this person developed within the last year or the last 2 years is not migrated to another institution with them, but actually is remaining in your lab. And that is something that we want because we have invested money, we have invested time, we have invested training in this. So I'm also going to revisit a typical scenario. A analysis workflow that a lot of people do is open package X, click, 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 drag, click, click, right click, save results.csv. Then that is load that result CSV into Excel, click, drag, generate graph, right click, save beautiful graph 1. But what goes into the paper is very different. It is the data was analyzed using package X, using the UI analysis, and the results are shown in figure 1. So there is, like all of those clicks, all of those dragging and loading and saving are not reflected whatsoever in what is actually reported in the figure, in the paper. A better technical scenario would be to have a complete chain of custody or provenance from your raw data to your finished results and figures. So at any point, you should be able to figure out which exact code and data version were used to generate which result. You should at every point be able to know where your graphs come from, where this amazing result came from. So you could have one single study, different versions of your study, and then, I don't know, if you finish your manuscript, you know what you used to generate the manuscript. If you're generating a first quarter report, a second quarter, a yearly report, you know how to get to those intermediate versions. If your research is really getting you the Nobel Prize, and you need that frozen version of your research that will do it, you can always refer back to it. From a practical scenario, imagine that you have all your data, all your research in your computer, and someone sneaks into your office at night and they delete every single thing, everything. Like, pretty much they set your office on fire. So you lose all of your data, you lose all of your code, but not really, because if you have it in a safe repository or in an archive, then you could get a new machine, you could go back home and generate everything using a single command. So a single command could get you back all your results, or your tables, or all your figures, and it would be great. The amount of time that we would spend or waste, really, in trying to reproduce all of these things that are not backed up or covered or versioned, is not going to come back. So, better yet, what if you get your dream job, I don't know, in Johns Hopkins, and you have to leave from one day to another? Or, I don't know, someone dies, and that is the one expert in a certain model. It would be great if someone completely unfamiliar will come up, pick up where you left or where this person left, and then understood why these things were built this way. From a sustainability point of view, thinking about reproducibility, thinking about provenance, thinking about all of these best practices helps us to speed scientific progress. It also gives back to our open source community. If you make your code open, if you make your data open, that will help someone else that will come after you and will only strengthen our community. You will also be forced to acquire more skills. You'll learn some other skills that, for example, other postdocs or other researchers or other data scientists don't have. So that gives you a competitive advantage against them. And it will also help to change the academic culture. And that needs a refresh. It really needs a refresh. And it also increased the buzz factor. So who here has heard about the buzz factor? Okay, a few hands. So imagine that you have a project that you're working on, a computational project. How many people need to be hit by this buzz before this project dies or stops or is unsavable? If you have a very small buzz factor of 1 or 2, you should really be thinking about reproducibility and increasing your project sustainability. But why is it so hard? I do also a lot of meta research. I care about reproducibility and I try to convince people, but I always find it very hard to go from A to B. And the truth is there are many barriers. Reproducibility is not considered for promotion. In traditional academic cultures and in structures, nobody cares if you have reproducible science or not. As I said, it requires additional skills. So you need to get additional training. You need to invest more time in your personal development. It takes time, but it depends also when in your research you start thinking about reproducibility. If you've done your whole study, if you've developed your most amazing machine learning algorithm and model, and after all of that you decide to adopt reproducible practices, it's going to take forever. Because chances are you will have to refactor a lot of that, you will have to double check, validate, and revalidate all of that. If you do it from day one, then the technical load should be much lower, really. There's also a high publication bias towards innovative findings rather than findings adhering to scientific rigor. Because of that, when you try and actually share research that is reproducibility first, it is held to higher standards to the innovative one because you are under the scrutiny and people can actually look at what you did. And there are many others. There are paywalled articles, so you don't have access to all of the research over there. Some people have started using the term of methodological terrorism, and there are also a lot of broken institutional processes. Also, a lot of people are afraid of sharing their data and their code because they are afraid that others will encounter errors. But I would say that it's better to find these errors early on. There are studies in which someone has developed a theory and then, 50, 40 papers reuse the same theory just to realize 40 years, 30 years later that it was wrong. So you have around 100 papers that are actually wrong because nobody verified the original theory. And also because we don't want to share. So a lot of researchers think, I spend my time, I train my people, it's my data, it's my code, nobody will get it because I'm going to lose that competitive advantage that I have. But there is hope. There is hope. There are a lot of people that are starting to care about these things. You can see the date there, that is on the 25th of June. The UCL is pushing hard, the UCL University College London is pushing really, really hard to start including these open science and reproducible science metrics into their promotion processes. So they will not only look at how many papers you're publishing, but the actual quality and the rigor of your papers. And I think that's amazing. That is great. It's much better to have, in my opinion, having 5 great quality papers, 5 stars papers, than 80 retractions as some other scientists out there. Where do you start? Sometimes I go and do a good job of convincing researchers to adopt reproducible practices, and then they get so excited and they're like, okay, so I want to use this amazing thing called Kubernetes. All the cool kids are using Kubernetes. Or, oh, I've heard about TensorFlow and I want to migrate my actual pipeline to use only TensorFlow. But some of the things that will have the biggest impact in your reproducibility practices are not the fanciest of or the latest of the technologies. You can start with very small practical steps. And these are worth millions. I've gone to academia, I've gone to industry, I've worked with big teams, with small teams, and this solves a lot of their problems before you actually go into the technical granularity that they need. Okay, when shall I think about reproducibility? From day one, I already said that. When you are designing your evaluation, diagnostic, and statistical methods is when you start thinking about reproducibility. When you start scoping your project, because that can allow you to think not only about your methodology and the tools that you need for your experimental phases, but also for your provenance phases. And this will also increase your chances of success. You can identify where you need additional training, when you probably need a consultant or a software engineer or a collaborator. Another thing is treating your digital research assets with care. The results are important, the results are great, and they go into papers. But all the processes that you followed, all the tools that you used are also important. All of those scripts that you say, oh, it's just the script to generate my beautiful graph are important. You use them anyway. So all your null results as well, your data sets, all your iterations can make a positive difference in research. So if you publish that, if you have a record of all of this, then probably the next person in your lab or in your group will spend less time going down that route that you know didn't work for you. Share with others. And what should be sharing with others? Well-documented code. Documenting your code is so important. Even if the only person that is going to look at it is you, if you go on holidays or you, I don't know, you decided you want to quit your job for 6 months and then come back, chances are you're going to be forgetting what you were doing. Also share the data that you use, the details of the workflows used, and also information on how people can cite this, if you're making it public and open, information how to use your work, and deterministic execution environments. In the sense that if people have the same code, the same data, the same environment, they should get similar results on a different machine. And sharing is not enough. I said it before, always, 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 always add a license. All your data, all your code have copyright attached. Making it public, let's say that you put your code on GitHub and have a public repository that anyone can access, is not enough. Because it is in a weird limbo. It is public, but you're not actually telling people that they're allowed to use, reuse, or modify your code. So a lot of people would rather not use it, and therefore you'll lose credit for your work as well. And when sharing data, add metadata, which basically is data about your data. And what you include here in your metadata is all of this information. where the data comes from, when was the data collected or processed, how you can access the data and how it was collected, what is actually in the data package, who collected, or if you have any questions about the data, who you can contact, and why is this data important, or when it was used. So if there are any other papers accompanying this data, you can add it there as well. And also, avoid this. Where is my data? Make things traceable. When sharing your data, make sure that you provide the data, the citation files, DOIs that are digital object identifiers and will identify your unique digital asset, and links to archives. And super important, also, if you're using somebody else's data, cite it, add information again on how others can access the data, and make sure that the links actually work. Make sure that when you click on those links, they exist. I know it sounds silly and it might sound stupid, but you would be amazed at how many non-existent links are out there. Version control is your friend. Everybody says that. Make sure that you version control your code, your manuscripts, your methods, your execution environment, and your data. But when I say data, your raw data are sacrosanct. You don't touch it. Not even with a stick, you don't touch it at all. You always have to have a frozen version of your raw data, unless you have data to which you keep appending, but you don't do operations, you don't do manipulations on your raw data. All your manipulations, your pre-processing, post-processing, training, recalibration are done in copies of that raw data, because if everything fails, you always have your raw data to refer to. And we also need to talk about consistent scientific data. When you share data, when you're passing your data to your collaborators, avoid sharing data using serialized formats like our data or pickles. We love them, they're lightweight, but they can break a lot between languages. They can break between versions. So when possible, favor CSV files, text files, JSON, and HD files. If you're feeling too self-conscious about sharing your work, get someone to look at it before. Use a linter if you don't have someone to look at your code. And choose the right tool for the job. If you're sharing a pipeline that needs to be run in a certain order, also consider sharing plain scripts and a workflow or a dependency graph. If you need to integrate both narrative and visualizations, use Jupyter notebooks or R markdowns for whatever you're doing. If you need interactivity, use tools like Binder. And I'm not saying that these are the only tools, but for you to have an idea on how to choose the tools. If you care about portability or usability, if you or your team find yourself copying and pasting and sharing code very often, why not considering making a package and open source it? And how much data, how much code shall I share? You start normally with the raw data and the pre-processing code. Then your pre-processed data and your modeling code. And this pre-processed data should always be combined with the pre-processing code and the chain of custody as well. If you're doing modeling, share your trained model and the evaluation code. And evaluation is very, very, very important, not only when it comes to your code, but also to your data. Make sure that you're validating your data at different steps. Make sure that the schema has not changed, that you're not getting weird numbers or weird things where you should be getting a certain data format. Excel is very well known, for example, for changing some genes into date format. Make sure that that is not happening at intermediate steps. If you are getting date intervals, make sure that you don't have a -5 years, because that is not a real time interval. It might be in the right format, but it doesn't make sense. And also, always add documentation and example cases. If you're providing your code or your packages and you're documenting it, provide one or two small cases, one or two ways in which people can get started with your package. And automate as much as possible. The less you rely on that click, drag, click, save, right click, beautiful figure, the better for everyone. And try to dominate the art of naming. Naming things is very hard. So go for these main goals. Make sure that it is machine readable so that it plays well with natural ordering or with grepping. So 0.01 clean data, 02 blah, 03. So when you open it on your Finder or Windows Explorer or do grepping on your terminal, it is easier to find things. Also make it human readable so that you don't have to open every single file to see what is inside there. So if I have a figure like length, tog versus interest, you know what I'm plotting there. Use universal structures and encodings, for example, for dates. Try to adhere to ISOs instead of using, what is it, month, day, year, like they do in the States. And also use delimiters intentionally. Make sure that you make sure why you're using underscores or hyphens. Don't leave spaces. And this will help a lot. Also, try not to use absolute paths when coding, but relative paths. And I know that I get this question a lot. So I'm talking about reproducible science and sharing things. So is reproducible equal to open? Not really. In many cases, there are a lot of people that can't share their data or their code because they work with classified data, or they work with patients, they work with criminals, they work with institutions. So you need to find something that works for you. Because openness and reproducibility is not only about disclosure. It's about this traceability of data that I was talking about. So you allow for your data and your code to be findable, accessible, interoperable, and reusable. So you can have fair access or fair objects without them being open. So when we talk, for example, about free access to journals, is that anybody in the world can download them and read them using, I don't know, Acrobat Reader, without having to pay for it. When we talk about open, we have these certain licenses that allow people to copy, reuse, modify all of the assets. But you can also have examples of fair data in which, for example, they can, in this study in Cambridge, they are making all of their assets fair. So it's findable, accessible, interoperable, and reusable. But because they have confidential data, they cannot make it open. They cannot share it to the public. But if anyone in a partner institution needed the access to the data, there is a mechanism for them to actually access it. So reproducibility is not exactly open. But you can still adopt an open science approach. And what does this mean? This means that you look at open access as and when possible. Make your publications open, your data open, your code open. But you also have to provide your people with training and education for them to aim to this gold standard. As and when possible, again, favor those open source libraries. If you can achieve the same with MATLAB and Python, favor Python or whichever open source if you have the alternative. Because that guarantees that more people will be able to access your code, run your experiments without them needing to pay for very expensive licenses. And that falls directly into equity, diversity, and inclusion. When you favor open source, that makes it more equitable for people around the world. Think about open data, and well, citizen science can only be applicable in certain domains. So you will see that reproducible science, open science, is not only about the science and the technical knowledge. It is mainly about the people and empowering them to make better science. Because so often we hear that we are the leaders of tomorrow, and we're not. We're the leaders of today. And by adopting these practices and investing in our people and investing in these best practices, then we can change the current structure. Doing open science and reproducible research can be hard, can be frustrating. Sometimes you feel like you're trying to move a 500-year-old ship, but unless someone like you, or like me, or like us cares an awful lot, nothing is going to get better. And that's where I finish my very long talk.